Okay, class. Today we're going to be going over some of the homework problems that are on your expert TA assignment. So first off, we're going to try to find the distance traveled in meters. I'm just going to pick a random one, and then we're going to go from there. So how about uh, since I'm since I'm holding the green marker here, we'll do the distance uh, d of our green arrow here. So as you can see, it starts from 6, and then it goes to 1 here, and then turns back around and heads to 4 here. So we can do 6 minus 1 for our first interval, plus 4 minus 1 for our second one. So this will give us 5, and this will give us 3. So basically you're just splitting this in half. And so we take this first interval from here, so this will be 1, and then the second interval here, which will be 2. And we just add those together to find the total distance that has been traveled. And so this will just give us 8 meters. And that's our distance solved. So next part of the problem is going to ask us about the magnitude of the displacement from start to finish in meters. So why don't we do? I mean, for the green one again, we can do this real quick, and we can just say that x is going to be equal to, well, we just have to take it from our starting or finishing point to our starting point. So we have 6 minus 4, and that'll just give us 2. So these are pretty basic problems that we're dealing with. We're just going over the very basics of this displacement. So now while we traveled 8 meters total, that's the distance we walked. Well, we only actually got 2 meters away. So like if you're going for, like, say, a run around the block, or around your township or wherever you live, if you end up in the same place that you started in, then your displacement is 0. In that case, you haven't gone anywhere. You might have ran 4 or 5 miles, but you've actually not gone anywhere. So your displacement is 0, while your distance would be 4 or 5 miles, however long you decide to run. Same thing with if you're talking about a track and field loop. If you're running the 400-meter dash, most tracks are 400 meters, if not all of them. So your average velocity would be 0, because you don't actually go anywhere in a 400-meter dash. Now, in a different scenario, if you're doing the 200-meter dash, you might have ran half that track, right? And you might have a really good time, but at the end of the day, the distance you've traveled is still 200 meters. But since the track is kind of sort of ovalish shaped, and you start here and end here, this is your displacement, while this is your distance. So there still is a difference between displacement and distance here. Another good example is, so if you're starting on the 100-meter dash, this is the only time that your distance and displacement are going to be equal to each other. Same thing with the mile run. That's just 4 laps around the track. Your distance traveled might have been a mile, but your displacement is 0. So now let's do this for a different one, just to show you. So now we have to talk about, so this was just our magnitude, right? We went 2 meters. But now we have to talk about if we're just talking about the displacement rather than the magnitude of this displacement, we have to account for direction here. So we were at 6 meters, and then we went back to 1 meter and then to 4 meters. So then our displacement is actually going to be, we have to account for that. And so then this is going to be 4 minus 6, which is going to be equal to -2. So in this case, we do have to account for direction. So you just have to make the distinction between distance, magnitude of displacement, and the displacement itself. So those are the 3 quantities you have to watch out for in this case. If we now move on to problem 2, we did something similar to this in our last lecture, but this is going to be a car problem where you have a car. I'm just going to draw it as a block because you guys already got the see my car drawing. And it's got a velocity v, and this is the positive x direction. This is the y direction here. And this is going to be v with our little arrow drawn on top. So now the car is moving to the left in a straight line in the negative x direction, travels the total distance d. So we have distance d is equal to, say, 16 meters. And during a time interval of, say, delta t is going to be equal to, I don't know, let's say 8 seconds. So what's the car's average speed in meters during the time interval? So all we have to do is we take v avg, and this is going to be the absolute value. And so then this is just the difference between x and t, and this is also going to be the absolute value here. So then we can replace delta x with d because it only travels in a straight line. And so then this is going to be 16, and then t is going to be over 8. And so this is going to just give us 2 meters per second here. And so now we are going to be asked what's the sign of the x component of the car's velocity at any instant during this given time interval. So we have our diagram here. This tells us that the positive x direction is pointing to the right, but we're moving towards the left. That means we're moving in the negative x direction. So if we were talking about just the velocity and not the magnitude of the velocity, we would be getting a -2 meters per second here. And so, then you're asked what is the x component, and that's what this would be. So this problem just built on one another. So it gave you the steps on how to find the x component of the car's velocity. First, we found the magnitude, then we found the direction, and then we put the two together here. So now this problem's a wild one. So let's see, we have, for number 3, we have assume an intercontinental ballistic missile goes from rest to a suborbital speed of 7 kilometers per second in 2 minutes. The actual speed and time are classified. What is its average acceleration in meters per second squared and in multiples of g. It wants you to use 9.80. I usually use 9.81, but I guess we can use what they want us to use. So all we have to do here is we just need to find our acceleration, and we can do that by saying, all right, well, it started from rest, so our initial velocity is 0, and it gives us our final our final velocity, and it gives us the time interval that it gets there in. So now all we have to do is what we say, all right, well, from our recitation notes last time, we have that A is equal to VF minus VI all over TF minus TI, but our initial time we're taking is 0, so we're just getting TF, which is just going to be delta T, which is the time interval that it takes to accelerate to this speed. Again, we have that since it starts from rest, this is also equal to 0, and so then we just get that this is going to be 7 kilometers per second, so we're going to write that as 7,000 meters per second, all over 2 minutes, so it's going to be 120 seconds. And so then this is going to give us a number, and I'm going to put this in Wolfram so I get it right. So we have 700 divided by 12, because you can just cancel out the zeros. And so this is going to be in meters per second. We can already do our units off the bat. And so this is going to give us 58.3 repeating. And so we can write that. So then other than that, oh, and it wants us to put it in terms of G. So all we have to do now is we have our acceleration, so we just need to take A over G, and so then we take 58.33 repeating meters per second squared, all over 9.80 meters per second squared, and that will give you the ratio of these two. So let's do that real quick. I'm going to chop off a bunch of zeros here. And so we have divided by 9.8. And this is going to give us 5.95. And so this is just how many times you can divide A by G. So now we can say that the acceleration in G's is going to be 5.95 G's. And we see that our units cancel out here, so this is unitless here, because this is just a ratio between two accelerations. Okay, so that solves that problem real quick. So next one has a bicycle race. You have an average speed of, let's say 17, let's go 16. So we're having an average speed of 16 miles per hour. I'm going to say, to heck with that. We're just going to use kilometers instead. So what we're going to do is we're going to say, all right, we have this bicycle that is going to be moving at, say, I don't know, 24 kilometers per hour. And so this is going to be our average speed. So I'm going to put V bar here. And since it's speed, we're just taking the magnitude. And so then we do this for 15 miles, or let's convert that to kilometers. We're going to do this for 21 miles, or kilometers, my bad. And after that, you must run for another 5.5 kilometers after you're done with the bike ride. So now we say, all right, with what average speed in miles per hour must you run for your average speed for the entire race to be a certain speed? So all we have to do is we can say, all right, well, we can just solve for this, right? So we can say, all right, we have this is our bike component. Let's draw this out. So we've got our bike here, and we take this at v bar for this distance, which is going to be a distance d, which is going to be 21 kilometers, and v bar is going to be 24 kilometers per hour, and this is the average speed of our bike over this interval. And then we have to walk. So on foot here, we have to walk another 5.5 kilometers. And so we can find how much time it takes to bike this certain interval here. And all we have to do is we have to take our distance and divide it by our velocity, and so, or our average speed, and that'll give us 21 over 24, which is going to be 7/8 of an hour. And so let's do that real quick. And then we'll take the decimal form and multiply it by 60 to get how many, or let's do 60. And so this is going to be 52.5 minutes that we are on this bike ride here. And so after that, we want our total speed, or our total average speed, to be, I think they give you, yeah, so let's do, we want our total average speed to be 16 kilometers per hour, right? And so all we have to do to find how much time that would take, we just need to take, because this is for the whole trip, and so all we need to do here is take our total distance, which is going to be this distance plus this distance, and then we need to take that and divide it by our average speed for the whole trip. So we can do that up here, and so we can say that d over v is going to equal, so this whole thing is going to be 26, and this is going to be 26.5 all over 16. And so this is kilometers. This is kilometers per hour. And so from here, we just need to take this. We just need to plug these numbers in. So we have 26.5 divided by 16. And so that's going to give us 1.656. So let's do 1.66. hours. And so now we can convert that into minutes. I'm rounding here, so, but this is going to be 60 minutes for the 1 and 40 minutes for the 0.66. So this is going to be 100 minutes here. And so now we have found how long we want our entire trip to be. So this is T, I'm going to write this as T total, and this is T bike, TB. And so now we need to find T running. So we just need to subtract these two. And so this is going to be 100 minus 52.5, have the 0 there, 5, 7, 4, 47.5. And so then we just need to take, because this is going to be our time in minutes that it takes to walk this or run this 5.5 kilometers. So we just need to put that into our calculator. So we take 5.5 and divide it by 47.5, and that's going to give us, so let me write that out for you. So we're going to take 5.5 divided by 47, because this is x over t. And so that's going to give us 0.11. And so this is kilometers per minute. And so now we're probably going to want to take this and put it into kilometers per hour. So we have 60 minutes in an hour. And so then we need to multiply this quantity by 60. And that's going to give us 6.95 kilometers per hour. So we have found our walking speed or our running speed that we need to travel. And that's it. Okay, so we're going to take our acceleration function here, and for problem 6, what we have to do is we have to take this function and get a expression for the velocity as a function of time. So what we can do is we just need to first integrate this. So integrating this side, a of t for dt, this is going to give us our velocity function here, v of t, plus an initial velocity. I guess you can put it on the other side. Yeah, let's put it on the other side. We're just going to get a of t on this side. And so then we'll integrate this side. And so here we'll have 6t. And here we'll have 2.0 t cubed all over 3. And then we'll have a plus c, but in this case our plus c is going to be our vi. And so now we have our velocity function here, and it says that we're given that our initial velocity is going to be equal to 0 because it starts with rest, and so we can just get rid of that because that's just going to be equal to 0. So now in order to write an expression for position, we do the same thing, v of t, and we're going to integrate both sides again. And so this is going to be 2 over 3 t cubed dt. Just to make things clearer. So then we're going to get x of t here. And so then we're going to have, this is going to be t squared, keep the 6 in front, divide by 2. So this is going to be, we can just get rid of this and put this as a 3 in the front. And then we can take this and we can go 2/3, and this will be t to the 4 over 4. And so now all we have to do is we're going to take our coefficients, we're going to put them together. So this is going to be 2 over 12, which is going to be 1 over 6. And so there we go. We now have our we also have to add on our initial condition for our initial position. And so if we're given that the initial position is 0, then this is just equal to 3t squared plus plus 1/6 t to the 4th. And then there you go. You're given your functions of velocity and position from our acceleration function up top. Okay, so this next question gives us this is going to be a velocity graph. And velocity is our function of time. And this is going to be t over here. So what we're supposed to do is we're supposed to construct an acceleration graph from this graph here of the velocity. And this is going to be units in seconds here. And so first off, we can see that the time derivative of v is going to be constant throughout this whole interval here from our origin to this interval here. And we can see that it's going to be negative. So if we were to draw an acceleration graph here, so this is going to be a, this is going to be s, this is a of t, this is s of t, or no, whoops, it's going to be t of s, where t is going to be in seconds. And so now we have, all right, this is going to be some acceleration here, and then we can see for the second interval that this entire thing is going to be positive. And so we can say that this is going to be, it's about the same, so we'll put it up, we'll put it right about here. But this one's going to be a little bit longer. Same thing for here. This is about the same, so we can put that here. It's going to be about the same slope is what I'm trying to say. And so we can keep on doing this because they have all about the same slope. And so this is what an acceleration graph would look like, building it from a velocity graph. Okay, so our next problem gives us a bike. And I'm going to do my best to draw a little bike here. And it says that it's initially at rest, so VI equals 0. And then it says it accelerates for a time t, which we're going to give as 9 seconds, at a rate a of about 1.5 seconds. So now what we have to do is we have to calculate the distance in meters that the bicycle traveled during that period. So we just need to take our kinematic function, and or our kinematic equation for xf is equal to 1/2 at squared plus vit plus x naught. We're going to take the point where it starts at rest, and we're going to consider that the origin, so x naught is equal to 0. And VIT is going to be equal to 0 because it starts at rest. And so then we can just get our position from this function here. We're given all of our variables, and so we can do this quite quickly, actually. So we have 1/2 times 9. I'm going to rewrite this as 3/2 just to make it simpler. So 3/2 squared, which is going to be 9/4. Yes, 9/4. So then we're going to get, this is equal to 1/2. 9 times 9 is 81. All over 4, so that's going to be 8. So this is going to be 8/81. This is going to be a little bit less than 10. So this is, or a little bit more than 10. So this is going to be 10.125 meters. Okay, so next up we have in a slap shot, a hockey player accelerates a puck from a velocity, initial velocity, to a final velocity in one direction. So part A says if this shot takes a certain time, calculate the distance in meters over which the puck accelerates. So we're going to accelerate this puck from 7.5 meters per second to 40 meters per second. I'm going to choose those as our values. This is going to be VI, this is going to be VF, and the time for T, I'm going to make that, say, 3.5 times 10 to the negative seconds. So we had our one kinematic equation, right? Where x is equal to v naught t plus 1/2 pt squared. And so we have our initial velocity in here, but now we just need to find a. So a in this case, we can say is going to be v minus v naught all over t. Or we can say that this is vi and vf, and there would be a delta there. This is just the time interval delta t, which is this t here. So we can plug in this a into this equation here, and so now this equation is going to look like x is equal to v naught t plus 1/2, and so one of these t's is going to cancel. I'm just going to take away this delta, but t is our time interval that we're given here, and so we plug in this. One of the t's is going to cancel, and we can just say that this is vf minus vi times a single t. And so a couple things we can do here. We can distribute our half in and our t's in. So we have v naught, I should say that this is vi, vit plus 1/2 vft minus 1/2 vit. Combine like terms here. So this is going to be, and then I'm going to factor out a 1/2. So we're going to have 1/2 vi plus vf t. Now you can see here that this quantity here is just our average velocity here of our puck. And so then we can say that the distance it takes to that this puck is accelerating is then equal to, and then we can just plug in our numbers. So here we have our half out in front multiplied by 7.5 plus 40, which says that should be 47.5, and then t is going to be 3.5 times 10 to the negative second. Now here we can see that we have meters per second, and then this one is seconds. So this should give us our x value. And so now let's plug this into Wolfram to see what we get here. So we're going to have this is going to be 3.5 times 10 to the negative second multiplied by 47.5. Oh, I made a mistake. All right, there we go. Not in this, but on my calculator. Okay. So then we get that x is going to be 8.831 meters. Again, meters per second, meters. Yep, that makes sense for this problem anyway. Okay, so the next problem up is a 100-meter dash problem. So for the first 13 meters of the race, the uh, the sprinter accelerates at a certain acceleration, which we'll say is a is equal to 3 point, let's say, I don't know, 5. Let's just make things nice and even, I guess. And then over that, after that interval, he has constant velocity for this rest of the race, and that velocity will be v. So our first part of this problem wants to say what's his time going to be for the entire race. So first thing we have to do is we have to find out, all right, well, we know that he accelerates for this portion of time, and we have to find out what his velocity is going to be at that point. So what we can do is, let's say, I think we can use this one. So we have Vf squared is equal to Vi squared plus 2a delta x. And so our delta x is going to be our 13 meters. Our Vf is going to be the V that he runs the rest of the race with. And Vi, since he starts out of his sprinting blocks, is going to be 0. So then we just have that Vf is going to be equal to the square root of 2a delta x. So now what we can do is we can just start plugging and chugging and get our final velocity here. So Vf is going to equal the square root of 2 times 3.5 times 13. And so this is in meters per second, this is in meters. And so that's going to give you meters squared over second squared. And so when we take the square root of that quantity, we get meters per second. So our units are correct. So then we have to take 2 times 3.5, which is 7, times 13. So 70 plus 21 is 91. So we have to take the square root of 91 meters per second. And that is going to be our Vf. So now, with this newfound knowledge of what our velocity is going to be for the rest of the race, what we can do is we can say, all right, well, we have d is equal to vt, and so then we can just solve for t. So that's going to be v over d. So then we just have the square root of 91 over 87, and so then t is going to be equal to that. This is going to give you somewhere around maybe 10 seconds, right? Okay, let's see. Oh, and then we have to add the time that it took for him to accelerate here. So this is going to be just the time interval for this part of the problem. So then we can take square root of 91 divided by 87. All right, I found the issue in my formula. It should be d over v. So we get to flip this. So this should be 87 over square root of 91. So that will then just give you, I'm just going to invert my formula in Wolfram. And yes, okay, that's way better. It's going to give you 9.12 seconds for this interval here. And so now we have to find the time it took for him to accelerate there. And so this is a a similar problem to the hockey problem. So, except that this one is just going to have it as it's going to be so we can use our formula from before, where it's 1/2 VF plus VI times T, and so we know what X is, and VI, since he starts from blocks, is going to be equal to 0, and so then we can say that T for that interval here, I'm going to write this over here, so T for this interval here is going to be equal to 2x over VF. Check our units. We have meters over meters per second, so the second is going to come up to the top, the meters are going to cancel. So we have time as our unit here, and so 2 times 13 is going to be 26 divided by 3.5 is going to be I'm just going to think about the answer for a second. All right, so I was plugging in A for VF, and that was my problem. So VF is just square root of 91, and so that'll give you 2.73 seconds. So now you just got to add them up. 2.73 plus 9.12 is going to give you 5 here, 9 here, and so he's going to finish this race in a district qualifying time of 11.95 seconds. Okay, so the next problem that we have is a car is about to speed past a police officer, and so the police officer is he has his speed trap. He's at rest. He's at one of those highway maintenance roads, I guess they're called, or the unauthorized access roads. And so we're going to say that this driver is going a constant speed of 120 kilometers per hour, and the cop starts from rest, so VIC is going to be equal to 0, and so this velocity that the car has is going to be completely constant here, and so we have to find the distance and the time that it takes for our police officer to catch his speed trap victim. So at a constant speed, the speeder is going to follow this equation, where this is going to be his velocity, and then we have the distance that he's going to travel and the time it's going to take for that police officer to come up and catch him. Since the police officer starts at rest, we can use our XF is equal to, we're gonna set XF equal to D, just to keep our variables consistent, because this is going to be the distance that both the police car and the speeder are going to travel. And then we have 1/2 AT squared, and then he starts from rest, so our VI component goes to 0. And since we're just talking about distance, and we're going to say that our initial X is going to be equal to 0, So we can also cross that term out. And so let's erase these guys here. And what we can do here is we can set both these equations equal to each other, and that'll cancel out our d's. And so then from there, we can solve this equation for t. So we're going to have vt is equal to 1/2 at squared, and we're going to give this police officer an acceleration of, let's say, 9 meters per second squared. And so we can cancel out one of our t's, get rid of the square on that side, multiply both sides by 2, and then divide by a. So we're going to have 2v over a is equal to t. And so now we can plug in our variables here, and we get that the time it takes for the police officer to catch the speeding motorist is going to be 2 times 120 all over 9. And so actually we're going to change this from meters per second to 9 kilometers. 9 kilometers per hour per second. Yeah, okay. Yeah, that makes sense. So he's going to gain 9 kilometers per hour per second. So a little bit of a different unit here. So we have to make sure that we take into account for those. And so we're going to have this guy's at 120 kilometers per hour. So now kilometers cancel, hours cancel, seconds is 1 over s here, so that gets flipped up to the top. Okay, so then t is going to equal 240 over 9, which is going to be this is going to be 26.66 repeating seconds. And so now we can plug this number into our distance formula here. So then d is equal to 120 kilometers per hour times 26.66 seconds. And so now we're going to have to convert hours to seconds. So what we're going to have to do is we're going to have to take hours on the top and divide this number by 3,600. So then d is going to be equal to 120. Oh, and also we can make this a little simpler too by converting kilometers to meters. And so that's going to take a factor of 1,000 out. And so what we can do here is we can, instead of multiplying this by, multiplying this by 3,600, we can multiply it by 3.6, because it's going to be 3,600 divided by 1,000, and then 26.66 seconds. And this is going to be meters per second here. And so now let's calculate what we got here. So let's go 120 times 3.6 times 26.66. And so we have a fairly large answer, so I'm just going to convert it back to kilometers here. So we're going to get 11.52 kilometers. And if you think about it, this is going to be a little over 6 or 7 miles, right around there. So if you think about it, this guy is really moving, and the cop or the police officer is starting from rest. So it's going to take him quite some time in order to catch up to this motorist. And so since we don't have a cap on the police officer's velocity, we can also figure out what his ending velocity was by multiplying the time it took to catch the motorist by our acceleration here. So then we can say that V F C is going to be equal to A T, and so then that's going to be equal to 9 times 26.66. So I have a sneaking suspicion that this police officer is going to be flying down the road. So 20, nope, I have that in there, 9, okay. So yeah, he's gonna be going close to 239 or 240 kilometers per hour, which is pretty darn quick. I'm gonna end things here. The last 3 problems, we've all done certain cases of these problems in the previous lecture, except for maybe the last question, which is I think a good place to stop, because you guys are going to need to think on this one a little bit. But make sure to take a look at problem 16 earlier than the others, because it does have 3 parts, but you guys should be able to solve it with your notes from class and the notes from recitation.